Right, I was able to make some progress. I've defined this new function, fit algorithms v3. Fit algorithms v2 also works, but I want to show you some new things on this one. So if I run source here, you can see the graph works now. It has the initial parameters here, and the values between 0 and 1 here, and the values between 0 and 1 here. That's good. And here are the final parameters, and the final parameters are quite close to the initial, so it means that we're making a good initial guess. Probably don't need to do better than that. You can see the fit is very close. One cause for concern is this number and this number. This is the intercept and this is the slope. It means that there's a slope underneath this. There's a linear function besides the two Gaussians. So what I would like you to do is plot the two Gaussians and the linear function on this same graph. And now I know that you had trouble doing this graph. What I ended up doing was using something called matplot. You can see what I did here. I couldn't figure out how to do plot with lines. It seems like I have no idea what the problem is. Everything looked fine. I have no idea what the problem was. Let's see. So where was the plot here? So let me find that plot. Okay, yes, okay. So this is what you do. You create a data frame with all of the functions that you want to plot, and you put them all in the same data frame. There was a problem here. We had integer instead of as integer, so that was causing a problem. But that isn't what prevented the plot, because even when I fixed that, it still didn't work. So here I created a data frame, and this is the first function I want to plot, h rescaled. And then I also want to plot the two Gaussian functions, so I add those as columns to the same data frame. Then I use matplot. These are the x-coordinates that are used for all of the vectors in the data frame, and these are the vectors in the data frame. If you look at ViewDF, you'll see that these are the original function and the two Gauss functions. Okay, so I hope that you can plot the final curves based on these final parameters in this plot here. So we can see how this black curve breaks up into Gaussians and a linear function. Now you may have to set the y-scale from 0 to 1 so that these plots show, but you should be able to do that. What R does is it sets the y-scale automatically according to the data. But if you use the method I mentioned and put everything use matplot, it will scale automatically. So that means you'd have actually 5 functions in the data frame. These two functions, well, I don't know. These seem to be working. I'm not sure why these worked and the other didn't work. Really not sure why that's true. You can try to do the same thing here, except with Gaussian functions, and see if there's any problem with that. So that's the first thing to do. Second thing is, I did mention that I think that we need to change the way we do the rescaling. Right now we have a rescale fund. Let's see what it looks like. Okay. Right now what we have is these are basically the x-coordinates. This is the function. This is what we want to multiply it by. Then we have these two indices, min index maps to 0, max index maps to 1, and inverse equals false. I think it's better to do a general rescaling function, where instead you do something like this. So you'll have your x-coordinates and your h, which is your function. Then here I'll have a in, b in, c in, and a out, b out, c out. So a in is the amplitude of the function. So in other words, h equals a in gets transformed to h equals a out. So this is the initial value of this is the initial value, reference value, and this would be the final reference value. Okay. So that way it's more general. We can use the same function, same rescaling both for the function and the inverse. To do the inverse, we simply reverse the order of the a in and a out. So, we also apply linear transformation to x, which is something we went through. I want to apply a linear transformation to this vector x such that if the value of x equals b in gets transformed to the value x equals b out, and the value of x equals c in gets transformed to x equals c out. And this is a linear function. You have to figure out the coefficients of that linear function based on b in, b out, c in, and c out. Okay, so you'll use b in, b out, c in, c out to get the coefficients of that linear function. Then you'll apply that linear function to this vector here. So a in and a out only apply to h. B in, b out, c in, c out apply to x. Right? You should also document this function in the function documentation that we have here, the algorithm description, just to make sure that it's there and it's understandable. All right, so that's the next step. Now, when you create this new function, you should create a new functions file, functions v3. And because we have a working version, let's just leave that alone. If we don't finish these modifications, we can still show the v2 to Dr. Harvey. Right now, I realized in going forward that we need to change the variables that we use. So what we're using now, when we specify the Gaussian function, I don't know why this is doing x. I thought I fixed that. It's just, it seems to unfix itself every time I fix it. Let me see if I can, I think there's something wrong with the software. Well, anyway, yeah, I'm not sure what's wrong with that, but I'll try to fix it one more time and see if that helps. And then I'll take this here and move it here. Okay, let's see if that works this time. I really thought I fixed that. Okay, maybe a bug in Word. Okay. So let's go down here. All right, this one's fine. Maybe I just missed those two. All right. Those Fourier transform, that's something different. Those are not Gaussians. And this stuff, we'll just leave it around in case we need it. All right, so here's the Gaussians that we're using. All right, so these are the Gaussian functions that are the constituents. These are kind of the bumps in the frequency that I have in the picture up here. You have Gaussians here. The purple ones are Gaussians. And we add them together to try to get our original function. We consider that our original function is somehow a sum of Gaussian functions. So we're trying to fit those. All right. However, I realized that in the literature, they don't specify the variables this way. Instead of having e to the minus am times j minus am squared, instead of having the am2 like this, they have 1 over 2 times am squared. All right? So we're going to rewrite all the expressions involving the exponential. Instead of writing it this way, well, I can do one for you here. Instead of writing it this way, and it's not letting me do anything here. Let me see if I can do this. We're going to write it this way, and then divided by 2a m3. I think I can do this. Yeah, okay. So I'll write it this way. I think I need another parentheses as well. I think if I close the parentheses here, it will do that. Yes, okay. So we want to rewrite it this way. Right? I'm going to change it back because I want to make sure that everything is consistent. Right? But you will change that am to this. So that means the meaning of this am2 is changed. The meaning of am2 is changed. So we still use am2 as our variable, but now am2 signifies something different. But what that means is the other equations involving exponentials also change. Of course, this is going to change, this is going to change, and this is going to change. Now, you have to be very careful about this because I'm taking the derivative with respect to the new am2. and not with respect to the old AM2. All right? So you can do change a variable. If you have trouble with that, you should go back to the original expression here, substitute in the substitution I made. Instead of AM2, have 1 over 2 AM2 squared, and then figure out this derivative, because everything now is going to be in terms of this new AM2. And you can see also there's something wrong with these indices here that you can fix. Those are not right. So that's the change we want to make here. Eventually, we're going to redo the rescale exp function. I think we can talk about that next time. All right. So in the documentation, replace the current AJ2 with 1 over 2 AJ2 squared. So we're changing the meaning without changing the variable, the names of the variables. So that means you don't put a, in here, for instance, in here, you don't put a 1 over 2 AM2 squared there, because we're still using AM2 as our variable. We're just changing the meaning of AM2. Right? So you can see that's the J there is not. Right? So that's a bunch of things that you can do. Things are really working out very nice. And I can tell you the next step is that I've been told that Gaussian function is not the final word, that there's another function that we'll be using, and that's called the Voigt function. And to do the Voigt function, we're going to have to get into complex functions. So that's going to be something new. But the basic idea is not going to be changed. The only thing that's going to change is the definition of G. Actually, the definition of small g is going to change. Instead of using a Gaussian, we'll use this Voigt function. But the way we have this set up is that nothing else needs to change. So that's a good thing. So that's kind of overview of what should be done next. And let me know if you have any questions.